Welcome, ladies and gentlemen, to the group exhibit Hydrogen and Fuel Cells and Batteries here on Hannover Fair 2015. Welcome to our public forum where we have interviews every 20 minutes here on stage and with your participation. So if you want to, you just can ask your questions. You can have a coffee or a cool drink here on the house and have fun with our next discussion, which will be all about electrolyzers. Electrolyzers is a very interesting technology right at the moment, and we have a very excellent specialist for that here on stage. We will talk about development potentials for electrolyzers and their role for the future energy systems, and we have the head of department Electrochemical Energy Technology from Deutschen Zentrum für Luft und Raumfahrt e.V., the DLR, the Institut für Technische Thermodynamik, here with us, Professor Dr. Andreas Friedrich. Very good to have you here.
Yes, hello.
Professor Friedrich, please have a seat. And just feel free, if you have a question, just raise your hand. I'll come down with the microphone directly to you. Professor Friedrich, let's talk about the German Energiewende, the transformation, energy transformation. It has one big problem. We have too much renewables, you could say. We have, and we need a storage system which is large enough, which is flexible enough. What could that be?
Yes, so certainly we will, with the increasing amount of renewable energies in the sector, and we know all the plans of the German government for the so-called Energiewende, for the transition to a renewable society, that we will need flexibility options. And one flexibility option that I find very attractive is the generation of hydrogen, because hydrogen can be used in very different applications. One very important one is, of course, mobility. So we have the possibility to transfer renewable power to mobility, but also you can use hydrogen. It's very important for the chemical industry. So in the long term, I see also the necessity to generate this hydrogen used in the chemical industry by renewable energies.
So whenever we have a surplus of energy in the grid, you would use it for electrolyzers then?
Right. Not all. So there are also other flexibility options like power to heat, if you need heat. But one especially interesting in my point of view is hydrogen, generating hydrogen.
But then you have the hydrogen, and as many people know, hydrogen is, very dense in energy, but it's also very voluminous.
Yes.
So what can you do with the hydrogen then?
Yeah, you have several options. So you can either have a centralized or decentralized implementation. A centralized, for example, could be to use salt caverns, which are available in northern Germany. Have a centralized hydrogen
where we
production.
have the wind power, so that fits very good together.
Fits very well. You don't have to transport the electricity too far away, and you can generate then hydrogen for mobility. But also, if you have chemical industry, you can also use it there.
Well, so what we really need is only the electricity. We have already. We need some water, which is available almost everywhere, to produce the hydrogen, and we need the electrolyzers in between.
Right.
That's the problem at the moment, isn't it? We don't have these high volume scale electrolyzers, or do we?
We have it, but of course these electrolyzers were developed for different kind of application, for the industrial application in former times. So they can be further optimized, and that's actually one of our main research topics, is to improve the presently available technology to improve efficiency, also durability and flexibility of the electrolyzers.
So I could imagine that with renewables there are certain problems also, because the wind is sometimes blowing very strong, sometimes very low, sometimes the sun is shining and not shining. So you have a high range, you need a highly flexible electrolyzer who can correspond to that. So rapid changes, aren't they a problem for the electrolyzer, for the durability of electrolyzer?
Yes, essentially I have to say that the electrolyzers can perform under fluctuating conditions, and we have demonstrated that a long time ago in my group with a large demonstration project, High Solar, where we coupled directly alkaline electrolysis with photovoltaics. So without a connection to the grid. So we demonstrated that's possible, but of course you have to take care that some operational aspects of the electrolyzer can lead to higher degradation. So you have to be careful in the design of the system and also the basic electrolyzer technology.
That's the point. The basic electrolyzer technology could be different, could be PEM electrolyzers or alkaline electrolyzers. There's a difference. Could you tell me a little bit what is better and what is worse?
Well, the alkaline electrolyzers are the mature technology that we also know from this High Solar project I talked to you. So they are very robust, essentially. They have also very good durability, but of course they are not as dynamic, and they're quite bulky, I have to say. So that's one disadvantage of alkaline electrolysis, and also their system design is somewhat more complicated because they need a KOH circulation, which makes the system a little bit more complicated compared to the polymer electrolysis, which is a newer technology, which still needs to scale up, but we see here a lot of effort to scale up this technology to larger sizes. And this technology has the advantage that it has a very high power density. It's built very compact, and therefore has also a lot of potential for cost reduction, in my point of view.
So if it's, as you said, the alkaline is bulgy, it's probably not a good opportunity for applications in Germany if we go into high scales. We don't have that place. We maybe in the desert somewhere. We could do that.
Well, yes. If you imagine that, for example, if you want to provide a fueling station with hydrogen in a decentralized way, then often you have very problems with space in inner cities, for example. Then clearly the polymer electrolysis technology would be of advantage compared to the alkaline. The alkaline is still, however, much cheaper. So polymer electrolyzer technology needs to reduce their cost.
So the next time you would propose it will be both together for different applications. Some will use PEM electrolyzers, others will use alkaline. Yes. They have their advantages and disadvantages. What I've learned about alkaline electrolyzers is that the electrode coating is crucial. So if you have too many on-offs, you get a permanent oxide coating, and that would not be very good for the anode.
Right, yeah. So essentially, even though it's a very mature technology, there are possibilities for improvement. And one thing that we are doing at our research center is that we are developing electrode coatings that increase the surface area of the electrodes so that the efficiency of the electrodes is improved. So you have less heat produced, and therefore we can actually make also the whole system cheaper, because if you have a high efficiency, you also use less electricity for the amount of hydrogen you produce, and therefore your electricity bill is lower. This is one point. Another thing is also we are working on improving the dynamic range of the alkaline electrolyzers, because at present their range is limited due to the crossover of gases from the anode to the cathode and cathode to the anode, meaning hydrogen and oxygen and hydrogen. And this we can do by certain innovative designs, which we also show in our booth, where you have a specific electrolyte circulation that avoids this crossover or reduces the crossover, and therefore permits to use an alkaline electrolysis system in a much wider range, operational range.
Is that the hollow membranes you
Yes.
show at your booth
Yeah.
right over
Yeah,
there?
over there, yeah.
That is a result of a project with the EU together, Resolizer,
Right.
wasn't it?
Yes, it's called Resolizer. It's together with Hydrogenics and the Flemish Research Center Vito. Here we have developed a hollow membrane where the electrolyte is circulated through the membranes and goes then through the electrodes. And this circulation reduces the crossover of gases.
It's also because the alkaline electrolyzer doesn't like partial loads,
Yes.
and you can cope with partial loads much better now.
Yeah, right.
Okay, very
The
good.
partial load is a problem for the alkaline electrolyzer.
If you have any questions, just raise your hand. You'll be with the microphone right with you. Just raise your hand, and you can ask your question whenever you like to. So another thing you have developed is anode and cathode coating based on Ranai nickel for higher efficiency, also for alkaline electrolyzers.
Right, yeah. So this is the electrode coating I was referring to. Nickel is a metal that is used in the alkaline electrolysis. By coating with a Ranai nickel, which is a nickel aluminum alloy, and then dissolving the aluminum in the KOH solution, you achieve a very high surface area electrode. And this very high surface electrode is much more efficient than a flat one.
And you not only invented the right coating for that, but also the way of putting it on it.
Right,
so
yeah.
this the vacuum plasma spraying that you invented.
Yes, so the vacuum plasma spraying is a method where we use a plasma with very high temperatures, over 10,000 degrees C, and inject powders there which are melted and deposited with high velocity on a substrate. And with this method, the advantage is that you can coat large areas very fastly. So we think that in an industrial production this will be very feasible.
It's quite interesting for me that with such a mature technology like alkaline electrolyzers, you can improve so much more. Is there much more to do, or are you at the end right now?
No, there are many things that you can think of. There's, of course, also other compositions of electrodes which we are investigating. But yeah, we will see if they are
It's still in the
successful.
pipeline. Okay, you wouldn't like to talk about it. Okay, very good. There's another question.
Good afternoon. What's your idea about the solid oxide technology for electrolysis?
Yes.
Thank you for that question. I would have taken that also. You
Yes,
wouldn't have?
so we are quite technology open. So we are working also on the solid oxide electrolysis technology. The solid oxide electrolysis technology works at about 800 degrees C, so at elevated temperatures. This, from a thermodynamic point of view, has advantages because you can use part of the heat for electricity production. So you achieve the highest electrical efficiencies with this technology. And therefore, we are working very hard to develop it. However, this technology is less mature, so we still need some development stages. For example, we need to improve the durability. Degradation rates are still higher compared to low temperature technologies.
I've heard that you reach 90% efficiency with
Yes.
solid oxide electrolyzers. Is that possible? That's really great, isn't it?
Yeah, that's possible with solid oxide electrolyzer technology. But of course, the heat management is a further complication because you need heat, a heat source to, for example, to evaporate the water you have. And this is something that has to be solved, but I think it's possible. Yeah, and we will work on it.
But I've seen I've heard of an electrolyzer, solid oxide, which is reversible. So
Yes.
you could use that one also as solid oxide fuel cell, and that produces heat. There's the heat you need, huh?
Right. So that's another idea that we are following in the project, is that we want to build a so-called reversible power station, meaning that we use the electrolysis mode with the same reactor, which is possible, to store hydrogen and to take heat from a heat storage medium. And then in the fuel cell mode, we generate current or power and provide heat in the storage medium. So it's completely reversible from the heat and from the electrical part.
And you have the same device for producing the hydrogen and giving it back to the power grid when you need it. So
Right,
it's very cost effective then in the end.
Yes. So the idea is to take surplus electricity, which is cost effective for the electrolysis mode, and then provide with the fuel cell electricity to the grid during times where it's highly valued.
For me, it sounds like the perfect solution, actually, as for a power to gas solution. So you can store the gas on site whenever you need it, and make the reverse process when you need energy. And even if you need more energy than you have produced before, you can take the gas from the natural gas grid, because a solid oxide fuel cell takes any gas.
Yes, right. Yeah, completely right. Yeah, that's a very flexible, fuel flexible.
It's like a dream reaction, isn't it?
Yeah, yes. But of course, it's a complex
it's
system
still complex.
and
we have to store the heat as well as the hydrogen.
Yeah.
Very nice. I like the idea very much. And there's another question.
Hi, I was just wondering, what sort of storage system would you recommend would be good to integrate with this electrolyzer fuel cell system?
Thank you for that question. Yeah, what
for the storage
for the hydrogen? I think you meant. Yeah.
For the hydrogen.
As you already mentioned, the salt caverns would be a good storage system,
yes,
wouldn't it?
For a large plant, salt cavern would be a good storage, so that would be pressurized gas. In most cases, we are looking for pressurized, but also metal hydrides are interesting, and probably you're also interested in that. For specific applications, metal hydrides have very good reversibility and are very safe systems, so that's very attractive too.
But you need a lot of metal to store there.
But you need a lot of metal, but for decentralized systems, I could imagine that's also a very attractive solution.
So one more idea with the solid oxide, as you know, it's my favorite idea probably, with the solid oxide electrolyzers, is you could, even in this high temperature, produce CO from CO2, which is another advantage, isn't it?
Yes, this is an advantage of the high temperature, that the same reactor, probably we need to adapt a little bit the electrodes, but the chemical composition of the electrodes, but due to the high temperatures, we can also drive other reactions. And one interesting reaction is carbon dioxide reduction, meaning CO2 conversion to carbon monoxide, and therefore you can provide a synthesis gas which is used to form higher hydrocarbons, meaning liquid fuels.
And if you put a Fischer-Tropsch behind that, then you even have liquids in the end.
Liquids, yeah.
That would also change the whole picture, so we don't need a new infrastructure then.
Right. In the long term, this is probably something we have to do, because we will need liquid fuels due to the high energy density. For example, for aircraft applications, we will need synthetic fuels, liquid fuels for aircrafts. It's not hard to imagine a gas fuel for aircraft, and therefore at the end, when we complete this transition, we will need synthetic liquid fuels, and the SOEC technology is perfect for providing this.
But you wouldn't say we will have in the future still liquid fuels for internal combustion engines, but these liquid fuels are coming from hydrogen, from renewable energies?
Yes.
Okay.
And taking CO2 from the atmosphere.
And taking CO2 from the atmosphere.
Yeah,
so consuming CO2.
From other sources. Yeah.
Excellent. Okay, any more questions about that? Yes, I'll come.
The SOFC operates at high temperature. So I would assume that it takes a while for this cell stack to ramp up and down. Do you think that is suitable for renewable energies, where, for instance, wind can come up very quickly, or the sun can start shining quickly?
Yes, you're completely right. This is one of the challenges, of course. We need the high temperature, so we cannot allow the stack to cool down too much. Otherwise, it would not react fastly enough when surplus energy is available. So we can allow the stack to cool, say, to a temperature level of 500 degrees C. And from that temperature level, the stack can very fastly heat itself up. But that's the case. We have to maintain a minimum temperature level.
Any more questions from your side?
But you can do that, with good insulations, you can do a lot, yeah.
So we should also talk about PEM electrolyzers. We didn't touch that field.
Yeah.
You already also have expertise in that field. So the problem with PEM electrolyzers is the catalyst, I would say. This is the expensive part, and
Yes.
we have platinum in there, and I've learned that. We even have iridium in there, which is very seldom, isn't it?
Yes. For the oxygen side, iridium oxides and ruthenium oxides are the best catalyst, but of course iridium is very rare, and nowadays high metal loadings are used, and we think for this technology to be really widespread, we need to reduce significantly the amount of iridium in the reactor, and therefore we are working also on catalyst development. And one approach that is well known for the fuel cell area is to use supported catalyst. What this meant is that you use a support and put very small particles, catalyst particles on top of it. And this is the approach we are following also for the electrolysis.
Is it you do it on both sides, also for the platinum on the anode side? No.
And the platinum is on the cathode side, and the electrolysis.
I always
mode.
mix that up. Sorry.
But that there's no problem, because here we can use the fuel cell catalysts with very low loadings anyway. So the real problem is the anode side on the electrolysis, which is this oxygen side, and there you cannot use the traditional fuel cell catalysts because they corrode.
And there's really not much iridium on this Earth.
Yeah.
We only have that from meteorites that came down here.
Yeah,
so it's very urgent, this work you're doing there. Yeah. But you found a way to the solution.
We found a support material,
right,
which is stable, and this is really from our point of view, the breakthrough to reduce the metal loading.
You also did some work on the bipolar plates. Normally you have titanium bipolar plates, which is also very cost expensive. What can you do there?
Yes, there we use also the plasma spraying equipment, which we use for coating of the alkaline electrolyzers, but now for producing coatings, titanium coatings. So this means titanium is a really stable metal under these conditions. However, it's quite expensive and difficult to machine. And so we would like to use stainless steel coated with titanium, and this coating has been developed in the last years. So that's really dense, and we get the properties of titanium on the surface, but with much less amount of titanium.
So as we can point out, you have expertise in any kind of electrolyzers, also fuel cells. So are there any more questions from your side? Well, in the end, we get some hydrogen from it. And it's always the discussion, what should we do with the hydrogen? Some say, well, we can methanize it. Others say we make liquids from it. Others say we have to use it directly for mobility. What is your opinion?
So my opinion is that the clearest business case is certainly as the mobility. Because as a fuel for cars, you have, say, you can charge, or you have a higher value for the fuel. But certainly if we have this transition and we want to reduce further the CO2 emissions, also in the industrial application has to be on the basis of renewable energies. And this, I see first the mobility area, then the industrial area, and probably at the end also the heat area, which can be delivered by hydrogen. So hydrogen really has the advantage that's a very flexible fuel. So
you really believe in a hydrogen infrastructure, and the hydrogen could be produced at every refueling station with an electrolyzer. How do you think the filling station will get the hydrogen?
There are two different possibilities. If you have enough space, you can have a decentralized electrolyzer at the fueling station, for example. But sometimes also fueling stations are in very crowded areas in inner cities, and therefore I think that probably also you need some pipeline systems, which may be local or which may be adapted from the natural gas system we have already. So if you don't need natural gas anymore, you can use it for hydrogen, convert it to hydrogen and use that. And also trailers, of course, will be a possibility for centralized hydrogen generation. So a salt cavern, then you have trailers that provide the hydrogen to the fueling stations in the neighborhood.
Well, so Friedrich, I've now learned we need electrolyzers to produce the hydrogen, but we use the sun for our solar panels to produce electricity and then to produce hydrogen. Why not going directly from the sun to hydrogen? Is that possible?
In principle, it's possible. So there are cells that produce directly from the sunlight hydrogen. So of course, internally they convert it to electricity, but then they make electrolysis on them in the same cell. These are the photoelectrochemical cells, they are called. They are quite attractive. A lot of people work on it, but there are still some issues that have to be resolved. And one of the main issues there is corrosion. So durability at the end of the cells.
Okay, I'm looking forward where the DLR will work in that field. So we have more to talk about next year. It was a pleasure for me to have you here on stage. I thank you very much for your attention, for your questions, and I thank you very much, Professor Friedrich, for this talk.
Thank you, Ulrich.
Pleasure. Well, please visit the booth of the Deutsches Zentrum für Luft und Raumfahrt just opposite here. Ladies and gentlemen are waiting for you just for interesting talks there. And we have the next interview here at 2:20, which is right now, with Dr. Christoph Avril, General Manager of Mahitec SRL, about Mahitec solutions for hydrogen storage. So stay tuned.